Let's now go to a very special case whereby I make the two charges equal in magnitude but opposite in sign, and we have a name for that. We call that a dipole. The plus charge is here and the minus charge is there. Situation is extremely symmetric, as you would expect, because they have equal power. There's one air blower upstairs and one vacuum cleaner downstairs. If you're close to the plus charge, notice that all the field lines go away from the plus. And if you're close to the minus, notice that all the field lines come in on the minus. You expect that. If you are far away from this dipole, now you have a problem. Before we had a +3 and a -1, and when you're far away, the +3 wins. So it's like having a +2 charge. If you're far away, you always expect the electric field then to be pointing away from the equivalent charge of +2. But if you add up plus and minus and they have equal magnitude, let's say +1 and -1, you get 0. So neither one wins if you're far away. And notice carefully, if you're very far away, indeed you do not see arrows either pointing out nor pointing in. Nature cannot decide. There isn't one that is stronger than the other. And that makes dipole fields very, very special. In the case of the +3 and the -1, if you're very far away, it's like having a +2 charge, and the E field, when you go further and further out, will fall off as 1 over r squared. With a dipole, your intuition sort of tells you that it will probably fall off faster than 1 over r squared. And that is part of a homework assignment that you have this week. In fact, I can already give you the answer. You have to prove it. If you're far away from an electric dipole, the electric field falls off as 1 over r cubed. It goes faster than 1 over r squared. There is not a single point in space where the electric field is 0. And you can think about that, why that is the case. So these field configurations can be rather complicated and can be very interesting, and each one has its own applications. Are dipoles rare in physics? Not at all. In fact, they are extremely common. You cannot avoid them. Remember last time I told you, if you have a spherical atom or you have a spherical molecule and you bring that close to a charge, let's now think of it, you bring it in an electric field. It's another way of saying the same thing. So we have a nice spherical atom or a nice spherical molecule, and we bring it in an electric field. The electrons want to go upstream the electric field vectors. They go against the direction of the electric field. And the positive charge wants to go in the direction, wants to go downstream. And so, what are you going to do? The electrons will spend a little bit more time on one side of the nucleus than they would in the absence of that electric field. And therefore, you are, through induction, turning that atom, turning that molecule in becoming a dipole. If you have a little bit more charge on this side, averaged over time, you have the same amount of extra charge plus on that side, averaged over time. So you make dipoles very often, whether you like it or not. And later in this course, we will learn more about the polarization of atoms and molecules creating dipoles when we talk about dielectrics. And you will see that it will have can have an enormous impact on the properties of the material.